Welcome to this explainer. Okay, I am absolutely thrilled to have you here today because we're about to pull back the curtain on something that is, honestly, just fascinating. We all see the flashy AI chatbots, the stunning generated images, the whole shebang. But today, we're diving into the hardcore systems engineering that it actually takes to make AI work in the real world. It's a totally different ballgame once you leave the cozy research lab and hit live production servers. It's literally reshaping how we think about software, hardware, and just the entire future of engineering. Let's get into it.
So let's kick things off with the elephant in the room. You see it everywhere online. It's in every beginner coding tutorial. Python is the undisputed language of AI, right? Well, we kind of have to ask ourselves, despite all that hype and massive popularity, is Python actually the language powering AI when we're talking about real, physical production servers and edge devices? To wrap our heads around this, picture a Formula One race car. Python is basically the design studio. It's the wind tunnel. It's where researchers sit with interactive notebooks and high-level math to prototype the aerodynamics and draw the car. But when that car actually has to get out on the physical track and win the race, that's C++. C++ is the engine, the chassis, the transmission. In the AI ecosystem, Python totally dominates the research phase. But the exact second an AI idea has to become a real product, where it's fighting strict memory limits, exploiting vector instructions, and squeezing every drop of efficiency out of hardware accelerators, C++ is suddenly everywhere.
And that crucial pivot point, that's what we call inference. Inference is simply the process of taking a live, already trained AI model and putting it into production to make predictions on totally new incoming data. When we shift from training a massive model over months to actually running it in real-time inference, AI completely stops being just a theoretical math problem. It instantly becomes the ultimate systems engineering challenge. It demands absolutely rigorous optimization.
Seriously, when you look at the sheer scale of the friction happening under the hood, it's just mind-boggling. We always hear about these massive models with billions of parameters, right? Well, think about what that actually means in a live environment. We're talking millions, sometimes billions, of arithmetic operations just for one single request. That puts extreme, intense stress on the CPU cache hierarchy. It causes huge memory fragmentation over these gigabyte-scale tensors. And the absolute kicker here? You have to do all of this within strict, non-negotiable millisecond latency budgets. The literal physics of the hardware becomes your biggest obstacle. Getting this memory management right is exactly why your AI chatbot can reply almost instantly instead of leaving you staring at a loading spinner for 5 minutes.
To actually hit those insane speed requirements, we have to look way past standard architecture and get into some extreme hardware and software co-design. We aren't just talking about writing faster algorithms anymore. We're talking about custom FPGAs, field programmable gate arrays, executing logic as parallel combinational circuits. We're talking about kernel bypass networking. Basically, this means completely skipping the operating system's sluggish network stack so your applications can talk directly to the network interface card. Literally every single microchip, cable, and line of code has to be perfectly aligned to shave off mere nanoseconds.
Okay, to really grasp this terrifying level of speed, let's look at high-frequency trading. It's an industry that perfectly mirrors these extreme AI production constraints. In HFT, the benchmark for a competitive system, the P95 wire-to-wire latency, meaning 95% of the time your system absolutely has to execute within this limit, is often under 50 microseconds. That is 50 millionths of a second. 50 millionths of a second to pull in raw market data from a network card, normalize it, run the pricing engines, and route an order back to the exchange. AI inference and things like autonomous driving, real-time robotics, and financial trading, it is now pushing right into these exact same insane latency brackets.
But all these intense constraints lead us to this really fascinating twist. Up until now, we've basically established that AI is this massive, heavy workload demanding incredibly optimized systems, right? Well, here's what I like to call the meta pivot. AI is no longer just the workload sitting on top of the system. It's actively becoming the systems engineer's co-pilot. AI coding agents are literally changing how we write the very systems code that runs AI in the first place.
And here's the deeply ironic truth about how these AI agents actually learn. You'd think they'd want perfectly clean textbook code to learn from, right? Actually, scratch that. As the source material highlights, real-world tasks reward familiarity with ordinary, imperfect, lived code.
AI coding agents actually thrive on massive, messy legacy code bases. Why? Because that's where the real production scars are. That's where the weird system-level mismatches and the hacky hardware workarounds live. The AI needs to see how human engineers actually stitch these incredibly complex systems together when they were under intense pressure.
Which brings us directly to one of the most heated debates in modern programming, C++ versus Rust. Logically, you would probably expect newer, memory-safe languages like Rust to be the undisputed future of AI infrastructure. Rust is incredibly clean, it's safe by default, and it forces excellent discipline. But, surprisingly enough, AI agents actually prefer the geological depth of C++. While Rust is absolutely a phenomenal choice for new, greenfield projects, C++ just has decades of deep, messy legacy. And in the era of large language models, that messy legacy is actually a huge advantage because it acts as an incredibly rich, dense training corpus.
Let's break down exactly why C++ has this unique advantage for AI agents. C++ has a massive density of real production history. Think about the foundational AI infrastructure, things like CUDA for GPUs, Onyx Runtime, OpenCV. They are all natively C or C++. These AI models have ingested decades of complex CMake build files, real public bug fixes, and what we might call optimization folklore. Because C++ has billions of lines of this imperfect, lived-in production code out there publicly, AI models have a much richer environment to draw from. So when an AI agent suggests a fix in C++, it has millions of adjacent examples of how real engineers solved very similar hardware-facing problems.
Ultimately, the future of our industry doesn't demand strict language purity. Instead, modern systems engineers are navigating this highly effective hybrid world. We use Python for rapid prototyping, research, and super-fast validation of machine learning models. Then, we drop down into hardcore C++ for that rigorous optimization, memory control, and low-latency inference in live production. And finally, we bring in AI coding agents as our partners to help manage, refactor, and optimize all that complex, legacy-native infrastructure. It's just a complete, tightly integrated engineering loop.
And that leaves us with this final, genuinely provocative thought. If AI is already acting as our co-pilot, helping us navigate and write this complex, hardware-level C++ code, how long until AI can completely optimize its own underlying systems? Seriously, think about that incredible feedback loop. AI understanding the deep intricacies of cache locality, memory fragmentation, and kernel bypass, actively building the very systems that will build even better AI. It's a wild thought. Anyway, thank you so much for joining me on this explainer. I really hope this gave you a completely new perspective on the intense, invisible engineering that makes our AI-driven world possible. Keep learning, keep questioning, and I will see you next time.